In this video, we will discuss what is meant by escape velocity, what are its values on different planets, how to compare the escape velocity on different planets, what are the different formula for the escape velocities, on what factors the escape velocity depends, and on what factors the escape velocity does not depend. The definition is escape velocity is the minimum velocity required by any body to escape from the gravitational field of the Earth or from the gravitational field of any planet. Let us limit ourselves to the Earth. The escape velocity of the Earth is defined as the minimum velocity required by a body to escape from the gravitational field of the Earth. But the gravitational field of the Earth extends up to infinity. So immediately we may get a doubt that perhaps the escape velocity is infinite. That is not the case. Even though the gravitational field extends up to infinity, it becomes weaker and weaker. At very high altitudes, it will be almost zero. Hence, the escape velocity is not infinite, it has got some finite value. Then how to find that value? For that one, we may consider the principle of conservation of energy. Suppose capital M is the mass of the Earth and capital R is the radius of the Earth. Suppose a body of mass small m is projected from the surface of the Earth with escape velocity v. So here it has got potential energy minus g mm by r and kinetic energy half mv square. At infinite height, its potential energy will become zero. From definition, it is the escape velocity is the minimum velocity just to reach an infinite height. So at that infinite height, the kinetic energy is zero. So applying initial potential energy plus initial kinetic energy is equal to final potential energy plus final kinetic energy. We have minus g mm by r plus half mv square is equal to 0 plus 0, or half mv square is equal to gm by r, or we can cancel m here, then v square is equal to 2gm by r, or v is equal to under root 2gm by r. This is the formula for the escape velocity of any body. On substituting the value of g, mass of the Earth and radius of the Earth, we get the escape velocity as 11.2 kilometers per second. The escape velocity is different on different planets. On planet Neptune, it is 23.56 kilometers per second. On Jupiter, it is 60.2 kilometers per second. Okay, on the moon, it is just 2.4 kilometers per second. On the sun, it is 615 kilometers per second. We know that a dead star is also called a black hole. On a black hole, the escape velocity is equal to the velocity of light, that is 3 into 10 to the power of 8 meters per second, or 3 into 10 to the power of 5 kilometers per second. Now, let us see what are the factors which influence the escape velocity. From this formula, the escape velocity is under root 2 gm by r. 2 is a constant, g is a constant. That means the escape velocity depends on only two factors, mass of the planet and radius of the planet. It depends on mass of the planet, radius of the planet. Since different planets have different masses and different radii, the escape velocities on them are also different. It is independent of two factors. One is the mass of the body which is projected. In the final formula, the mass of the body is not at all mentioned. So whether it is a tennis ball or a cricket ball or a cannonball or just an atom, the escape velocity is same for all. It may be given like this. A body of mass 1000 kg has escape velocity 11.2 kilometers per second. If you take a body of mass just 1 kg, what will be its escape velocity? Same 11.2 kilometers per second. The escape velocity does not depend on the mass of the body which is escaping. It depends on the mass of the planet from which it is escaping. Second, it is independent of the angle of projection. Suppose on the Earth, a body is projected at 11.2 kilometers per second. Whether you project it directly upwards or at some angle, 60 degrees, 30 degrees, 45 degrees, or even at 0 degrees. If you project a body with 11.2 kilometers even at 0 degrees centigrade, it will escape. It may be asked, it may be given like this. If you project a body directly up, the escape velocity is 11.2 kilometers per second. If you project it at 30 degrees or at 40 degrees, what should be the escape velocity? You need not hesitate. The escape velocity is independent of the angle of projection. Of course, the body should not be projected downwards. From 0 to 90 degrees, for all angles, the escape velocity is same. This is because the earth is round. Is it okay? Now let us compare the escape velocities on different planets. For that one, let us consider the formula. Escape velocity is equal to under root 2 gm by r. Suppose you have got two planets of masses m1 and m2, radii r1 and r2. Then v1 is equal to under root 2 gm1 by r1 and v2 is equal to under root 2 gm by r2, and dividing one by the other, v1 by v2 is equal to under root m1 by m2 into r2 by r1. Suppose this is the earth of mass m, radius r, escape velocity is v, or sometimes here value will be given 11.2 kilometers per second. It may be asked like this. Suppose we have got a planet having mass twice that of the earth, radius same as that of the earth. What can be the escape velocity on that one? Only the mass is changed. Mass is doubled here. Mass is under root in the numerator. So the answer will be root 2 times v. Or if you want, you can use this formula. Or if you want, you can solve it directly. Suppose it is given like this. Mass is 4 times, but radius is same. Mass is 4 times. If you write 4 here, 4 under root will give you 2. So the new answer will be twice the old answer. Mass is same, radius is doubled. Radius is taken in the denominator. So it must be 1 by under root 2. Mass is same, radius is made 4 times. If this is made 4 times, 4 root is 2 in the denominator. So the answer will be v by 2. Or you can use that formula. Suppose mass is doubled, radius is also doubled. This is doubled, this is also doubled. They get cancelled. There is no change in the escape velocity. It will be v. Suppose mass is doubled, radius is half. This is 2 here, this is half here. This half will go to the numerator, becoming 4. 4 under root is 2. So the new answer will be twice the old answer. I hope it is clear to you. Now let us consider the other forms of the formula of the escape velocity. Before we do that, let us see one more thing. Suppose it is given like this. Keeping the mass of the earth same. If the radius is increased, the escape velocity decreases. Keeping the mass of the earth same, if the radius is increased, the escape velocity decreases. If radius is doubled, the escape velocity will become 1 by root 2 times. Radius is made 4 times, the escape velocity will become half. If radius is halved, the escape velocity will become root 2 times. If radius is made 1/4, the escape velocity will be doubled. That we understood. Suppose it is said that the radius is just increased by 1%. You see 1%, there is a root here. Whenever small changes have got power, the overall change is multiplied, that change into the power, multiplied by the power. So if radius is increased by 1%, escape velocity decreases by 0.5%. If mass is increased by 1%, escape velocity increases by 0.5%. If mass is increased by 2%, the escape velocity will increase by 1%. If radius is increased by 2%, escape velocity decreases by 1%. I hope it is clear to you. Now,